our discussion on network protocols. I guess we cannot make it today, so we will finish the topic next week. And then the week after, in our last class, we will talk about network performance. We will drop socket programming in this semester. To recap what happened the last time, which was in the week before Christmas, we talked about the network layer in the network protocols, and the most dominant protocol in the network layer is the IP protocol, the Internet protocol. Introduced, this is in fact astonishing, really impressive from my perspective, that these two people, Cerf and Khan, they like sketched or introduced so many important concepts in the mid 70s that are still of utmost relevance today. Um, uh, and this includes like the notion of how to scale a network, um, where we compose a network or where we compose a bigger network out of smaller subnetworks. So a network, so the idea of networks, that was proposed by Cerf and Khan in this paper. The Internet protocol, the IP protocol, was introduced in this paper, and the TCP protocol as well. So the whole TCP IP stack that we use in the Internet today, all um, came up and proposed in 1974 by Cerf and Khan, and they got the Turing Award for that in 2004. So we are discussing IP. IP has two major versions, IPv4 and IPv6. IPv6 is still ongoing, so the migration, the shift from IPv4 to IPv6 started in 2006 and is still ongoing. IPv4 still the dominant protocol that we use in the internet or in general in networking today. So we will take a focus on that. And the last time we saw how an IPv4 datagram looks like. So there are a lot of interesting fields in the header. One interesting aspect is that the addressing scheme in IPv4 is, on the first hand, global. So the network layer addresses, or the network layer handles addressing in an end-to-end context. So we are dealing with end-to-end transmission. So IP addresses are unique in context of the whole internet. And we have 32 bits to express one IP address. And with 32 bits, the highest number that we can express with 32 bits is 2 to the power of 32, which is in the ballpark of 4 billion IP addresses. And as a couple of devices or many devices have multiple IP addresses, we have a upper limit of devices that can participate in the internet using IPv4. And this is a limitation that is addressed in IPv6. But nevertheless, we have to deal with the 32-bit IP addresses. An IP address is just a number in binary, and we write this number up in a special format. Where do I have it? Here. So this is the dotted decimal notation, which represents this binary number in 4 bytes, and these bytes are separated by a dotted decimal notation. And the bytes, so the 8 bits in binary, are then represented in a decimal number. So this is how IP addresses look like. And an important aspect on IP addresses is, and this might be new for some people, is that an IP address has two parts. It has a network portion and it has a host portion. A network portion identifies the network the host is in, and the host portion of the IP address identifies the host within the network. And the network portion is variable in size. So you can have smaller subnets, you can have bigger subnets. And if the subnet is small, meaning we have a small number of hosts we can fit in the subnet, meaning the host portion is small and the network portion is bigger. So a big network portion means a smaller host portion means a smaller network. If the network portion, on the other hand, is small, then the resulting network can accommodate more hosts. So the network gets bigger. Um, and the network, so a bigger network that is composed of smaller networks. The smaller networks we call subnet because it's a subnetwork of a bigger network. And we are doing subnetting because we can handle smaller networks more easily as bigger networks. Naturally, we can manage smaller things way better than big complex things. So breaking up a big network into smaller subnet makes sense in terms of organizational effort. It makes sense in terms of routing because the routing problem is easier on smaller networks than in big networks, and also for security reasons because you can define security rules. So which devices, which persons can access resources in a subnet, yes or no. These kinds of rules can be written up and defined based on smaller networks and not based on bigger complex networks. So subnetting makes a lot of sense from different perspectives. A subnet is, in general, a consecutive range of IP addresses. Let me recap this concept real quick for you. Um, so as I said, this work? Yes, this works. As I said, an IP address is in fact a binary number, and there is a natural order in binary numbers. So we can order IP addresses, obviously, because it's just a number. So we can also like express then the range of IP addresses in an axis, right? Where we have 0.0.0.0.0 here at the top. This is the smallest number, the smallest IP address. And the biggest one is 255, 255, 255, 255. 255, because this is the highest number starting from 0 that we can express in 8 bits in 1 byte. So we can express from 0 to 255 with a byte. So this is the whole range of IP addresses that are possible. And then, so basically the whole address space of the biggest network that we can express. And we can segment this range. So for example, we can carve this segment out. Let me get another color. So this is green. Hopefully you can see this. And this is maybe a range from 10, 0, 0, 0 to 10, 255, 255, 255, right? So this would be a subnet of the bigger network, right? And we can do this hierarchically. We can further create subnets in the bigger subnet. For example, we can do this. This is 10, 10, 20, 0, 0 to 10, 20, 255, 255. And let me draw another one, smaller one. This should be 10, 250 point 200.0 to 10, 150, 200 to 55. Just as an example. And you can do this. You can nest this like hierarchical organization of subnets. But the important thing is that one subnet, like this, for example, it always has a consecutive range of IP addresses. And one bigger subnet can accommodate, host many smaller subnets. And how you segment a bigger subnet into many smaller subnets, this is what you can do by yourself. Question chat, are this numbering, is it randomly? Yes, yes, you can. You can specify this by yourself. You as a network like engineer or network designer, you can specify these ranges. But there are some certain rules which we learn today. But this is, I mean, this is subnetting, right? So it's a it's a segment of a larger network with a consecutive specific range of IP addresses. But this range cannot be arbitrary. One important rule is that the network portion determines the size of the subnet. And the network portion, it's the first part of an IP address, it's the first bits, and the length determines the size. Because if the, for example, network portion is, let me switch over here. If the network portion is 24, for example, we have a what IP address range do we use? We use this one, right? So let me split this up from 10, 150, 200, 0 to 10, 150, 200, 255. If we take this range, then the network portion are the first 24 bits. And these are 8, not 8, 3 bytes, because 1 byte is 8 bits, right? So the network portion are the first 3 bytes of the address. And the last 8 bit, this is the host portion. And you see it in the range because the host portion defines or define the range of IP addresses that are possible in the respective subnet or a specific subnet. The network portion does not change, right? So the network portion identifies the network and the host portion identifies the host inside that network. And as this is a bit length, the size of a subnet can only follow powers of 2. Because it's a bit length. With 8-bit host portion and 24-bit network portion, we can have 2 to the power of 8 hosts in that network. Or in other words, to be technically a little bit more precise, we can have 2 to the power of 8 addresses within a certain subnet. On the other hand, let me give you another example. This one. So the range of 10, 20, 0, 0 to 10, 20, 255 to 55, it has a network portion. This is not a nice bracket. It has a network portion of 16 bits and a host portion of 16-bit. You see, because the range is from 00 to 255 to 55. And the first like part, this one, this stays the same. This defines the network and the remaining bits define the hosts. And here it's 16, 16. question is how many addresses can be allocated in this kind of network. It's 2 to the power of 16. It's 65,500 and something. So the number of hosts that you can allocate inside a subnet follows powers of 2. The number of addresses is 2 to the power of bits in the host portion. Okay. I said, well, the number of addresses and not the number of hosts. Here we need to be very careful because there are two addresses typically reserved in a subnet, the first address and the last address. And we cannot use the first or the last address in a subnet for a single host. We need to assign a host we need to assign an address that is like in the middle of the subnet, not the first, not the last, to a host, because the first address is an identifier for the network itself, because you need to identify subnets as well. And for that, you take the first address in a subnet, and the last address in a subnet has a special role because this is the broadcast address. And the broadcast address does, as the name says, it broadcasts. So if you send a message or a packet to the broadcast address of a subnet, the device will deliver this packet to all included hosts inside this subnet. If you send one packet to the broadcast address, the message gets delivered to all the hosts inside it. It broadcasts the packets, so to say. So if I ask you a question, well, if we have a network that has a host portion of 8 bits, how many hosts can it accommodate? Question to chat. So if we have 8 bits in the host portion, how many hosts can we have it inside this network? Please put your answer in chat. It almost. Mini, almost. Sayed, yes, it's 254. It's 2 to the power of 8. This is the number of addresses we can have in the subnet, right? And we need to subtract 2 because we have the network address and the broadcast address. I guess 253 did not consider that we start counting at 0, right? But the number of hosts we can accommodate in a 8-bit host portion network is 2 to the power of 8, which is 256 minus 2, which equals 254. Another question, if we have a if we have 50-50, so 16 bits network portion, 16 bits host portion, how many hosts can we have in there? Consolidate my calculator as well. Exactly. 65,534 because it's 2 to the power of 16 minus 2. Okay. When we write this up in CIDR notation, CIDR notation combines the IP address with a slash followed by the length in bits of the network portion. Some examples here in the table. If we have a network portion of 8 bits, this means that we have 24 bits left over for the host portion, and the range goes, in this case, from 192.0.0.0 to 192.55.55.55. In /16, we have 16 bits, 16 bits. In /24, we have 24 bits in network and 8 bits in host. So the range for this subnet is respectively smaller. And if we want to identify a dedicated subnet, we write the network address, like the first address in the subnet, and then separate the prefix. So the number of bits in the network portion is also called the prefix. We separate this by a slash, and this would be the address of or the identifier of the subnet itself, not for a host, but for the subnet. And typically, you design the networks this way, where you have a subnet, for example, 192.168.178.0/24. Hosts have address inside subnet, like 219, 185, and so on and so forth. Inside a subnet, these hosts are connected together with a switch, and to reach like other hosts from other subnets, then you need to leave your local subnet, and the gateway for that is a router. Router has typically the first usable for a host address in the subnet. So the first address is reserved for the network itself, and the one after, like the ones, these are typically for routers. So in this case, this would be 192, 168, 178 /1. Before we go into subnetting, a question in chat. So why -2? Because there are 2 reserved addresses in each subnet, the network address and the broadcast address. We cannot assign these addresses to hosts. This is not allowed because the network address does not identify a host, it identifies the network, and the broadcast address has a special role. So we cannot allocate or assign IP addresses, the first or the last, to a host. So we need to do -2. Okay. So when we talk about subnetting means creating subnets in a larger network. So subdividing a larger network into smaller networks. And there are 2 design goals that we need to consider. What we want to do is we want to design the subnets such that we can easily expand them, because this is a common problem in network engineering. So network requirements shift over time. So at the time where you design the subnets, you may or you need to take into consideration that the parameters on which the design decision is made changes over time, and typically networks get rather bigger than smaller. And we need to keep that in mind when creating subnets, that in the future, there is a somehow big probability that we need to make the network bigger in the future. So we need to expand them. And also, we want to design subnets efficient in a sense that we do not waste addressable space. So we want to maximize the remaining addressable space, meaning that you want to minimize the allocated space when we create subnets. And achieving both is a balancing act. You see this in the example here. So if we have a network or a base network, which is this one, 192.168.0.0/16. And we say we want to segment this bigger network into 3 smaller networks. We can do this. So this is the bigger network, and then we allocate a smaller network at 192.168.10/24. So this ranges from 0 to 255. Then we do 190 to 168 2/24 and then 3/24. This is in fact a bad design because it violates our goal that we want to in the future expand the networks because they are in a sequence. The first network or the second network follows right after the first network, and the third network follows right after the second network. So if we want to expand the second network, for example, we cannot do that because the third network is allocated like in the range of IP addresses directly after the second one. Let me draw this real quick. What this situation is. Well, let's do it horizontally. Well, if this is our range and we have 192.168.0.0 here, and we have 192.100, oh, 92, not 99, 192.168.255 to 55 here. So this is the range. This would be 192.168.0.0/16 inside a notation. And the allocation would be as follows. We would have the first network here, the second network here, and the third network here. So this would be the allocation in the range. But you can not expand that. And this is an issue. So what do we do instead? I guess we briefly talked about it the last time. There's a method that is proposed by Cisco, and this method is called reverse binary. It's a method for a smart subnet allocation. And this is what I propose as well. So a lot of people do it wrong when designing subnets, and we do it right. We do it as proposed in Cisco, and to really thoroughly read through the method, you can refer to chapter 36 in the Network Warrior book. But the approach, it looks complicated, but if you understand the algorithm, it's not as bad. So the approach, the algorithm is as follows. Our starting point is a network that we want to segment, right? So we need a base network, and we need the number of desired subnets. So in the previous example, we had this as a base network, and we said, well, we want to allocate 3 subnets in this larger range. We need to know this before, and then we start to count. Starting from 0, we count in binary until we have reached the amount of desired subnets. And to express the count value, we use as many bits as the network's host portion. Then we do the reverse bit order. Then we do a mirror image of the count that we have just created and just reverse the bit order. So the last bit becomes the first bit, and the first bit becomes the last bit. Just a mirror image. And then we interpret this mirror image as IP addresses. And this gives us the starting point of the subnets that we want to create. Let's see this in an example. This is a minimal example. Please be aware, this is a minimal example and does not really make sense in practice because the base network is rather small, right? So this network that you see here, 192.168.178.0/24, it's a rather small subnet with 256 addresses, 254 hosts. Allocating 8 subnets in this small network in practice does not make super much sense, but I chose this example because it's small enough such that I can fit it onto a slide. Because in a /24 subnet, the network portion is 24 bits, meaning the host portion is 8 bits. So we count in binary using 8 digits, 8 binary digits. So when we want to allocate 8 subnets into this network, we count from 0 to 7. We always start counting from 0. So we have 8 zeros, then 1, 1 0, 1 1, 1 0 0, 1 0 1, and so on and so forth. So we start counting in binary, and then we do the mirror image. Then we reverse the bit order. So 0 stays the same because it's all zeros. But you see here in 1, the last bit in the normal binary 1 gets the first bit in the reversed binary. The second last gets the second first, and so on and so forth. So we reverse the bit order, we flip it, and we create a mirror. And then we interpret this as like decimal, meaning that a 1 and 7 zeros is 128. And we use this as the host portion. This gives us these addresses. And these addresses are like the boundaries for our subnets. So these are the starting points. These are the network addresses of our subnets that we want to have. And then you think about, well, how big should the subnet be? So at first you calculate the network addresses, and then you think about the prefix because the prefix defines how big the network is. And typically the recommendation of Cisco is, I mean, you need to have an initial idea how big the subnet should be, and then you take double because you need to leave some headroom for like future hosts that you want to put in the subnet and so on. Okay. This is how reverse binary works, and I guess we do the task right away. So there is a task in order to train this reverse binary method. Let's do this. There's a task in iLearn called network segmentation. And this network segmentation requires you to do a proper network segmentation. So imagine that you're responsible for designing a network layout. And let's do the DEX building. So if you're already in Germany and if you're already at campus, maybe you have been at the DEX building. It's close to the campus, but it's not inside the campus. And there are different use cases, purposes. For example, professor offices where we have 24 hosts. In the deep learning lab, we have 30 hosts. In the HPC lab, we have 28 hosts, and so on and so forth. And I want you to use the reverse binary method to create a subnet allocation within the 10, 112, 32, 0/22 address space for the table above, and leave enough headroom in the subnets to double the hosts as initially planned. For that, please recite the reverse binary method from the slide and then try to create a subnet allocation for this table. We do this in breakout rooms. So you can work in a group with 3 to 5 or 4 to 5 people. And you will have how many time, or how long do you have for that? Let's do 20 minutes. In 20 minutes, we talk again. Is there any question before? Then talk to you in 20 minutes. Oh, welcome back, everyone. Um, oh, yeah. Now people are coming back. Uh, so unfortunately, my migraine gets worse, and I don't feel that I can continue the lecture. I have to lay down, unfortunately. I have uploaded the solution to the network segmentation task on iLearn, so you can check if your solution fits to the solution or to the reference solution. And I guess we will continue our classes next week. We will have to reduce in scope a little bit, but this should be fine. Okay. Yeah, sorry for the abrupt break, but I think I have to lay down now. Yeah, talk to you soon. Bye bye.